So, well, I was thanking the organization for this nice invitation and the privilege of being here. And so, as Professor Campos said, I'm from the University of Barcelona. And so we do in Barcelona mainly synthetic chemistry. And so we've discovered a method to produce heterometallic lanthanide compounds. And so we are using them for helping and contributing to the proposition of using the magnetic spin for quantum computing. So quantum computing, Fernando Luis already mentioned quite a lot about it in the previous talk. I'm not going to extend myself on introducing the concept of quantum computing, just emphasizing key aspects. For example, when we compare quantum computing with classical computing, instead of having the classical bit as the minimum information way of encoding, we have in quantum computing the quantum bit, which has instead of having two states of a physical system, we have two quantum states of a quantum system. So we have indeed these two states to encode the position 0 and the position 1. But of course, quantum mechanics also provides resources that are not available in classical computing. And one of them, and one of the most important then, as also Fernando was mentioning in his talk, is the possibility of preparing quantum superpositions of these two states, an infinite number of quantum superpositions, which allow things that, of course, are not thinkable or attainable in classical computing, such as quantum parallelism and other resources. Well, any physical system can embody a quantum bit as long as it has two quantum states that are well defined, but there are also some requirements, as was laid down by Di Vincenzo, two quantum levels, as I mentioned, initializing possibilities, as it was mentioned also in the previous talk, scalability, the possibility of preparing many identical qubits, of course, the long coherence, which is what we need to preserve the quantum information while we need it for its manipulation and processing, and addressability, which is fundamental, perhaps the most difficult aspect of quantum computing, which is the possibility of writing and reading quantum information. Okay, so in terms of using the magnetic spin, well, we turn into chemistry. We want to use molecules to embody the quantum bits, and among the many possible ways we can do it, we can use lanthanides. Lanthanide ions, like this ytterbium center is here in the middle of this forest of atoms. Lanthanides in general, as I was saying, have a two-level magnetic structure, which is generally well isolated from the excited states, which can be used to encode the qubits. And there are advantages to lanthanides also, because they can be amenable to show good quantum coherence, and of course the chemical versatility. So this is what we like as chemists, and this is what we try to do. So, but there are other things, other nice things that have been discovered or enhanced about lanthanides when working with them as possible qubits. For example, in the case of gadolinium, which is, of course, the least lanthanides of lanthanides, because it doesn't have this strong spin-orbit coupling, so it behaves more like a transition metal. But this was used to understand that the eight states of its magnetic revalence state, 7 halves, can be used to encode the 8 combinations that you can think of when you have a 3-qubit system. So this metal can provide the computational basis of 3 qubits embedded into only one ion. So the small amount of zero field splitting allows also to address them individually because they are not equally spaced. So this has been a relatively recent development. And so we thought that we had an opportunity here to go one step further let me say that having 3 qubits allows us the possibility of undergoing 3 qubit quantum gates. For example, the so-called Toffoli quantum gate, which flips the state of the last qubit, target qubit, if and only if the 2 control qubits are in a given position. And so Fernando Luis and his collaborators were able to show not only quantum coherence on those transitions, but also for this particular transition, the possibility to prepare any quantum superposition, and this can be demonstrated using nutation experiments. Okay, so so in our case, we thought, okay, 1 gadolinium, 3 qubits, 2 gadoliniums, perhaps 6 qubits. Okay, so well, the only thing we need is to prepare molecules that have 2 gadolinium ions that are aware of each other through this weak magnetic interaction, but most importantly, that they are non-equivalent. So it is not it's not very difficult to make dinuclear lanthanide compounds, but it is a little bit trickier if you want them to be not equivalent. Okay, so in fact, we were, let's say, in possession in our laboratory of a system that allowed us to make dinuclear lanthanide compounds that were inequivalent using this ligand, which wraps metals into molecules. In this case, the ligand being inequivalent, the lanthanide complex, the dinuclear complex also, or the two metals also, will end up being equivalent. Now, indeed, the system is very versatile and well behaved, to the point that we're able to prepare this compound for an entire series of lanthanides, including gadolinium. So in principle, we have what we want, and it's a matter of see whether the properties are appropriate for this gadolinium ions to become a 6 qubit system. Okay. So in the meanwhile, or in this process, where we having the opportunity to examine in detail the structural parameters of this series of compounds that goes from lanthanide to lutetium, we were able to unveil a few interesting features, like the fact that, well, the lanthanide contraction, so these are bond distances or additions of bond distances, the lanthanide contraction is maintained throughout the entire series. But the interesting thing that we saw here is that when we compared one position with respect to the other, this set of distances in this position was systematically larger than the distances to the metal in the other position. Okay, so you see the lanthanide contraction, but you see a gap that is maintained throughout the series. Okay, so. Of course, immediately as chemists you think, okay, this might give you the opportunity indeed to prepare heterometallic dinuclear compound just by mixing in your reaction this ligand with combinations of 2 metals different in size. Okay, so this is what happens for a large amount of combinations, and so we were able to demonstrate throughout the years that we were able to prepare many compounds that are heterometallic with a high level of purity, as we demonstrated also through a variety of techniques. So let's say the main parameter that we have to take into account, of course, is the difference in ionic radius between these 2 metals. So when they become very close, indeed the selectivity breaks down, but the system is sufficiently selective to have remarkably pure compounds for metals that are not so different in size. So it's a quite a nice system that allowed us to enhance or put into value the properties of heterometallic systems like the one I'm going to show now. Because, well, let me just mention that one of the techniques that allows us to better ascertain the selectivity is mass spectrometry, and the absence in solution of any of the homometallic, or those are simulations here, the gray trace is the experimental, so the absence of any combination that is not the selected heterometallic one. Mass spectrometry. other techniques also. Okay, so here is our gadolinium, and so here is our possible 6 qubit system. And so in order to study in detail each of the ions in the absence of the influence, so without the influence of the other one, we took advantage of this methodology I just mentioned. And so we were able to prepare the analogs where the gadolinium would be isolated from the other one just by coming together with a metal that would be diamagnetic. So if we want to study the gadolinium in the large position, we just make the compound with an ion that has that is smaller than gadolinium, and when we want to study the other position, we just make the compound with a metal that is larger than gadolinium. Here lanthanum and here lutetium, both diamagnetic. So that allows us to investigate each position individually. And for example, those continuous wave EPR look very similar, but they're sufficiently different so as to describe each of the systems with two, let's say, sufficiently different parameters of zero field splitting. So that allows us to differentiate all these states that we want for our 6 qubit system. Okay, also to put into experimental evidence the coupling. In this case, it is not necessary to prove the coupling. We can just measure the susceptibility of the gadolinium, but we can compare it with what happens when adding the contribution from each gadolinium individually. Okay, so here is the spectrum, 64 states as expected for a 6 qubit system. Of course, there's a significant amount of crowding here. There's a technical problem to exploit these transitions, but nevertheless, here they are. For example, well, by studying the EPR of this system, we indeed realized that for a significant amount of magnetic fields, we have quantum coherence of those transitions. We also can see the difference very clearly between the system when we have only one gadolinium and let's say the 6 qubit system. So also the differences in quantum coherence, because we can use EPR also to determine the quantum coherence of these transitions by looking at the decay. And so also see that when we put both ions in the same molecule, we significantly decrease the coherence. And so in any case, we have here the 6 qubit system. Okay, so this is basically a synthetic method to prepare not only asymmetric systems, but heterometallic systems, which is what we really like as synthetic chemists. So we tried to exploit this method to go one step further. So basically, this method is based on exploiting the differences, let's say, combinations of these two chelating pockets, a beta diketone and this, let's say, tridentate pocket. Exploit different combinations in different coordination sites, so that by having different numbers of these two types of pockets, we enhance longer or shorter bond distances. Okay, so combining two ligands that feature indeed both of them, these two types of pockets, we ended up with this scaffold. This is a complicated molecule that has, in fact, well, two of these ligands and two of these ligands here, binding to metals in a way that in the central position we favor very strongly large metals, and on the side positions we favor then the smaller metals. Okay. So indeed, this is highly selective. This is a mass spectrum showing only one, let's say, trace, not any other combination of three metals in here. Originally, we reported these three analogs with cerium in the middle and various smaller metals in the sides. And more recently, we have been able to characterize quite completely these other combinations. So here is just a more detail of the mass spectrum, where in color simulations of the various combinations, and in gray the experimental one showing only the expected one, which is in this case is the lanthanum, which is this one here. Okay, green. Okay. Luckily, it was the right one. Okay. So now comes the most, let's say, scary slide of this presentation. Okay, this is the result of a collaboration with Professor Stefano Carretta from the University of Parma, who saw in these molecules the opportunity to propose a quantum bit with a quantum error correction mechanism incorporated. For this, you need three qubits: the central qubit, the actual qubit, and two ancillary qubits. Okay, and to do a quantum error correction protocol, what you have to do is to perform a series of quantum gates. Okay, so let's say different transformations of your qubits on a particular time sequence. So there are two groups. There are two groups of operations. The one is called encoding. So it's composed of two qubit quantum gates. It's a control knot. So you use the central qubit in one of the ancillary, and then the other one, and some rotations of the superpositions of each of the qubits. So this apparently this converts your qubit into a phase protected qubit. So a protected qubit. Then you have some time to perform your quantum operations or to have your qubit with its quantum information in there. It's a memory time where you can have errors. Okay, but if you have done that before and then you perform somehow the inverse procedure, if you have had an error in here, this is something I'm not gonna demonstrate, but if you have had an error in here, by performing a last quantum gate, which is a quantum operation on the three qubits at the same time, a Toffoli, remember the Toffoli? So here you do a Toffoli where the control is the central qubit. This corrects the error, okay? I presume here we have to believe that, but basically what we are interested in is that our molecules in fact can do anything similar to this. So to show this, what we have to do is first characterize the Hamiltonian. Believe it or not, this is a very simple Hamiltonian. It contains the coupling between the three qubits and then the Zeeman splitting of each, let's say, effective spin 1/2 of each qubit. Okay, just this. And then so characterize this properly and see, using then the parameters of this Hamiltonian, whether by doing the proper simulation, Stefano Carretta, see whether that is a good system for protecting errors. So how we characterize the Hamiltonian? Of course, we do the magnetic measurements, thermodynamic measurements, EPR, specific heat. But the interesting thing is that we can take advantage of, again, the selectivity to study experimentally, individually, the properties of the central qubit by putting it next to two diamagnetic ions, lutetium in this case, as small metals, or to study the ancilla, the erbium, by having it come together with lanthanum. Okay, so this is what we as chemists can do. Okay, provide the opportunity to study the ancilla and the central qubit individually, as well as the ensemble. And so this is done with very meticulous investigations on magnetization, presumably also in the microsquid that Fernando showed some time ago, at very low temperatures, specific heat, of course EPR, and the same thing for the entire ensemble with the same techniques, and even post-EPR, which allowed us to evaluate the quantum coherence of some of those transitions. Okay, so for example, by having this Hamiltonian very well characterized, we can establish the energy spectrum of those magnetic system with the doublets connected to each other, which indeed fulfill the computational basis of three qubits, and showing some of the quantum gates that are mentioned from that circuit before that were necessary for the quantum error correction, including the Toffoli. Here the central one is the control that goes from 0 to 1 only if the external ones are 1. You see, 1, 1, 1, 1, and then the central switches. This is the Toffoli that corrects the error after performing all these other operations, which, by the way, are implemented using pulse TPR. It's a sequence of pulse TPR. And finally comes the simulation. So if you take this Hamiltonian that we have characterized experimentally, which is contained in here, we see what is the effect of the various pulses we undergo through that circuit, which is contained here, and contemplate all the possibility of errors, which apparently can be explained here. By following this sequence and undergoing this the integration of this equation, okay, over time, I presume, we can simulate. What we can do is establish the comparison between the error that you have if you apply a protocol, or with the situation when you when you apply it or when you don't apply it, without the protocol and with the protocol. For everything that is above 1, you have an advantage of your protocol with respect to nothing at all. So there are there is a large amount of conditions where you experience a great advantage of applying your protocol. It is better as the quantum coherence of your system becomes higher. This is, if you have this type of quantum coherence, you have better efficiency. And so, and also this is put as a function of the time of the memory time. So the memory time, of course, has an influence on it. So basically, with this simulation, we were able to demonstrate that this molecule with real Hamiltonian parameters indeed should provide for a good way of protecting the qubit. Only everything within one molecule. Okay, so basically, well, that brings me to the conclusions. So we made some compounds, heterometallic compounds, dinuclear and trinuclear, that can be exploited to show the requirements for various quantum gates. Here today I talked about the 6-qubit digadolinium system, and also about quite impressive qubit with an error correction mechanism embedded into one single molecule. Okay, so this brings me to the acknowledgements. I would like to thank the people in the lab that made those molecules over the years, now all doctors. These two started, Veronica and David started as PhD students, now are doctors, and Dr. Leonivarrios, who has overseen this research over the years. Our collaborators in Zaragoza, I think I have to change this this logo. I think now has been, it's called the Institute of Aragon, Institute of Nanomaterials of Aragon, Instituto de Nanomateriales de Aragon, Professor Fernando Luis and Olivier Beau, and of course Professor Stefano Carreta for the simulations. And finally, I would like to thank all the various agencies from Catalonia, from Spain, and from Europe for the funding. And I thank you for your attention.
Thank you very much, Guillem. Then the talk is open for discussion. I'm sure that Shelley will have some question.
Sure. Thank you for a beautiful talk.
Thank you.
Indeed, I have questions. So I got totally presentation. Then, so the quantum error correction, is that not only for trimetallic systems, or can you also apply this quantum error correction for the first sequence if you would have just 2 metals instead of 3?
Well, of course, this error correction protocol needs this sequence of encoding, decoding, and then correction. And the protection is you protect 1 qubit, which is the central qubit. And so you have this ancilla that by doing operations that combining with the central qubit, in the end, this ancilla allow you to identify an error and correct it. Okay, and so this involves operations with both ancilla. There are two single quantum gates that use sequentially one and then the other one. But the most important thing is that you use a Toffoli, which is an operation that uses the central as the target and the external auxiliary as the control, and a TOEFL has two controls. So you need two ancillary that control the central qubit. So you need three metals. But if you could put more than one qubit in one metal, like what we did with the gadolinium, you could use it. You could use only one metal. So we use this three trinuclear system by using each metal as one qubit. Okay, but I think Fernando Luis proposed the gadolinium ion already as a system to implement an error correction because it had 3 qubits in that setup. But of course, the conditions are different because you have in this gadolinium you have the 8 states that are very close in energy to each other. So I don't know whether the implementation would be easier with just one gadolinium ion or with one molecule like this. But in the end, conceptually, it's the same. Okay, it depends on how you encode the qubits. I don't know if. So basically, using metals that each one is one qubit, you need the 3 of them.
And the ancilla is the reverse sequence, basically. If I have like 19 Irving Lenton, then Irving Lenton, the metal choice for that.
Okay. Basically, the ancilla have the main requirement is that the ancilla is very different from the central one. Okay. Now, perhaps you could invert them, but chemically we cannot do it because we have to put the large metal in the middle. We cannot do it at all.
So the ancilla must be also then isostructural to the qubit.
The ancillary have to. In fact, they have to. Ideally, they have to be different because otherwise you cannot differentiate them. Cannot say, okay, now I'm going to do a quantum gate, a sealed gate with one ancillary. So if you see the diagram here, which is in order to have eight different states, the 2 ancillary have to be different. Otherwise, you cannot have 8 different states. And so in our case, they are. I mean, ideally they are the same, but they use the advantage that they have different orientations within the molecule. And so, using a magnetic field or different orientation of the magnetic field, you have them different. But chemically, they are identical. So that was a problem, but in the end, it was not.
We have another question now from Fernando Luis,
Okay.
because the time is running. Fernando, are you there?
Yes, thank you. Well, thank you, Guillem. It was very nice. So I have a comment on the previous question, I guess, is that you can use any system with 8 levels in principle that are non-negative space to do what you see here. But in fact, doing it with a qubit, for instance, in the gadolinium system, is more complex. So it's not so easy to find out the sequence of pulses you need. In fact, we are working on that, and you need a kind of library to translate this algorithm from one to another. So the two are in some sense equivalent, but the realization sometimes is more complicated, and I would say this implementation that Guillem has shown is simpler. And so closer to the realization status. So my question is whether you could also synthesize these beautiful trimers with gadolinium, or you have tried to, and where the gadolinium would go to the 2 external sides or to the central one?
Well, this is a great question. I mean, you're talking about only gadolinium or gadolinium with somebody else?
Yeah, gadolinium with somebody else.
Okay.
Yeah.
Now, we're trying. For the moment, we are reducing gradually the size of the large metal. Now we are, I think the smaller one is praseodymium, I believe. And then increasing the size of the small metal. So, did I say decreasing the size of the large metal? We want down to praseodymium, and increasing the size of the small metal. I think we did holmium. I think is the larger one. Now gadolinium, as you know, is right in the middle, and so ideally we would like to try the same thing we tried with the dinuclears, but the systems that we made are very, very highly selective, but are more difficult to make. So basically, we're trying, Fernando. I don't know if we will manage to do that, but in theory, you should put the gadolinium in the middle with the smaller metals in the sides. We can go into the details of the chemistry, but I don't think it will be a little bit too long. But
no. It was just because it would be nice also to this would be just a next step in this direction, and could be funny. And I mean, there are other ideas we can discuss this.
Okay. Coffee break or sometime soon we can try to discuss that in detail. Okay. Thank you.